Okay. All right. So, yeah. What I was saying that the bond. Had I started recording? Yes. This bonding can also be, we can relate this thing to that. It sounds, I mean, usually when we talk to this in the class, student would find it more funny thing, but that is the thing that actually when we are studying chemistry, right, when we are reacting to some reaction, some topics or some fun or any other emotions we are reacting to, what is happening? There are some chemical things changing in us, in our brain, in every, I mean, that's why we are reacting in a certain way, right? So yeah, we can relate this chemical bonding, our all other bondings, to the chemical bonding to some extent, but that is much debatable, and that needs much time and arguments to set. Anyway, so there will be different type of bonding in the chemical bonding we'll be learning, and our learning objectives for this is the formation and of chemical bonding between atoms. How do they form? Why should there be a chemical bonding? I mean, bonding formation of bonding formation, and why should there be a bonding in the first place, right? That is the thing that's the thing that we should know. And if there is a bonding, then what type of bond is? Can we categorize some bonding? Whether it's strong or weak or just bonding for the sake therefore staying together, or what type of bonding are they forming? Whether they are stable or not stable, all those things, and why they are behaving in that way. So the ionic, polar, non-polar, covalent bond, and all those things. There are some other bonds, metallic bond, van der Waals bond. So those things will also be discussed later on. And so after that, when they form the bonding, right, we will try to understand how this type of bond has been formed and what does this bond do to the structure of the chemical. All right, when they are forming the bond, how do they change the structure, or how do they shape the structure of the compound or chemical? So from we will try to know it from the Lewis structure to understand the Lewis structure. Of course, the dot and Lewis dot and octet rule will also be discussed. It will inevitably come in this topic to discuss. And when we are talking about the Lewis structure and the octet rule and all those things, there will be another thing, another topic that we have to discuss is the formal charge. The formal charge to predict the most likely, because in the Lewis structure, when you learn this one, or if you have gone through all these lecture slides, which are already been published on the canvas, you'll see that there can be many different possibilities of a Lewis structure, even though they fulfill all the octet rule and form the form the stable compound, but there are some differences in the formal charges of different compounds. So how do we predict, or which one should be the best bonding or most promising or stable bonding based on the formal charges? The formal charges are how much charge they share the compound is having at that moment. So if we just go back to the history a bit, if we just go back to the history of this chemical bonding, then we'll see that the chemical bonding did not just come in one day or just like it is. There is a history for this evaluation of chemical bonding. Okay, there is a history, and first, from the very early stage, people are very like you guys. We are all that why there is a different type of compounds. right? Why there is different apocomers, even though there are similar same element in different compounds? Why they are, why they feel, I mean, why they look different? Why their physical and chemical properties are different? So those things, those questions led to the investigation more into the how do they stay or how do they occupy that compound in their different state. Okay, so the evaluation of chemical bond, if we very briefly discuss that electrons and electrostatic force was the main precursor for explaining the chemical bonding. And when we knew that there are electrons, there are some particles called electron, and they are, we call bonding electrons, valence electron, and all those things. So scientists by that time, they knew, okay, so that the electrons are actually transferring from one to another one. Right. So if electrons are transferring from one element or one atom to another atom, and then they come together, stay together, are stable, that is called, by transferring of electron, we call it ionic bonding. Okay. And another one is valence electrons. That's not necessarily electrons are being transferred, but they are being shared. Both of, nobody is, I mean, none of the atoms are claiming that it is my electron, it is your electron, but they are just sharing the electron in the both atoms together, and by that sharing, they are forming the Lewis structure and octet rule that we will discuss later on, and by that way, they are forming covalent bonding. Okay, but again, there is much more modern, if you can say that, modern view of this chemical bonding by quantum mechanical approach. And from this quantum mechanical approach, the valence bond theory or molecular orbital theory has been evaluated. And for this case, though, we will not be discussing this valence bond theory, molecular orbital theory, but you will just touch a bit about it. All right. So types of interatomic bonding. There are different types of bonding. I mean, three main bonding. That is ionic bonding, right? There's ionic bonding, that electrostatic, that bonding happens due to the electrostatic attraction. Electrostatic attraction are the forces or the attraction. Is there any other word for this? The attraction they feel because of this positive and negative charge they form. Positive charge, how do they form the positive charge? By giving one electron away, right? The atom, if it gives or donates or share, I mean, release one electron from its atom, then it will form a cation that is positively charged. And another atom, if it takes the electron, receives the electron, or snatch the electron from that positively, I mean, that another atom, it will become negatively, that is called the anion. So that is by when there is a positive and negative charge, right? When there is a positive and negative charge, they will feel a force or attraction between them. Everywhere, the positive and negative, they always get together, right? And they are usually strong. When there is a charge difference is higher, the more stronger it is, right? So by this way, and that is called the electrostatic attraction between thus positively and negatively charged ions. And that is why they will form that ionic bonding. Covalent bonding, though, again, it is an electrostatic attraction as well between negatively charged shared electrons and positively charged nuclei of the atoms involved in the bonding. It not necessarily giving or taking the electron away from one another, but they are just in mutual agreement to share the electron both. Those who are more prone to share the electron, like he is okay, or that atom is okay to share the electron, it doesn't mind, but it not necessarily have to give the electron, because if it gives that electron, it is not very stable, but it has a tendency to release that electron, and somebody else, other atoms, has a different tendency, opposite tendency. So they will come to and say, okay, you don't have to share the, give that electron and become unstable. What you can do is just let's share together. So I will take those who are positively charged atom, they will say that I will keep more of it, but you also keep a little bit of it. So that is covalent charge, and that is why when there is not, they are not totally giving or totally taking the electrons. Some of the atoms are taking more of it, and some other atom, the other atom is in that bonding and not taking the okay to release more of the electrons. It will be, there is still there is a tension, or there is a attraction force between them, and that is why there is no pure covalent bond. Actually, I will see more about it when you go down, and there will be polar covalent and non-polar covalent bonding as well. Metallic bonding. Okay, so when in the metals, we have seen the transition metals, right? In the periodic table, we have seen the transition metals. The metals, they have d orbitals, right? They are d block, isn't it? If you have remembered it, yesterday we were discussing. They have d. So d block elements they are, and they have a sea of at the outer shell. They have a sea of electrons. Like they have too many electrons in the outer shells. When, let's say, the two metal atoms comes together and both of them are having a lot of electron in the outer shell or valence shell. So that electron, they don't have to share that electron. If anybody is too much electrons outer shell or valence shell, so if any of the metal needs any electron, they can just take from there. It is repository, not repository, but it is a bank. You can say it's a bank. If it wants, it can just take one electron from there and to form a bonding. Okay, so that is called the sea of electrons, and these metal atoms are able to take, if they need, they can take one electron from there. All right, so it says this is the three main things that bonding that we'll be discussing, and there are some categories in covalent bonding we will see later on, but each of the atomic bonding, if we want to see the interatomic bonding, if we want to put it in diagram, how will we see that ionic bonding? Let's say talk about ionic bonding first. Ionic bonding, here these two atoms are coming together, right? And let's say that this is one anion, or this is one atom that requires or is a very electron hungry, or it requires more electron to be more stable. So what it will do is it will take one electron from another atom which is okay to give the electron. Okay, which is okay to give the electron, and it doesn't mind too much, and it does not cause any trouble on its stability, or it becomes more stable by shedding the electron. So this electron will go here, all right, and what will happen is both of them will stay together by transferring the electron. By giving the electron, it is forming a bond with that negative ion. So one becomes positive, another becomes negatively charged. Another way that this electron, let's say that this is an electron hungry, and it does not have anyone nearby to give that electron totally to it, like this. It is a very good one, right? that it has given that electron. This is a good one, that it given the electron to it. But let's say that when it is alone together, I mean alone, and it does not have anyone nearby, a donor that can give, so both of them can come together and share the electrons. The same thing, both of them are same, and they come together, they are sharing the electron, and this electron is not a property like here. We see that both of the electron becomes the property of this B. Let's say it's alpha, it's beta. It becomes the property of beta. But for this case, these two electrons are, both of them are properties of alpha and beta together. So this electron will go around this atom and then also go around this atom. So this electron is, and same thing goes for this electron as well. So both of the electrons are for both of the atoms. But this thing always does not actually, this idea of forming the bond, sharing the bond, electron, and forming the compound does not always, make us understand the structure of the atom. All right, of the compound. So when more than one or two or three elements come together and then forming a bonding, what will be their shape or sizes, right? And even, we'll see later on, even if they are forming and sharing, looks like they are ionic bonding, they are forming, but actually they are not ionic bonding just because of their shape, right? So we'll see it later, but then this Gilbert Lewis, he is a professor, and he started to draw a diagram, on his lab books or log books in the lab. He used to work in the lab, and then he started to draw the diagram and put the electron, the valence electron. He was thinking that, okay, in the if we see, put the valence electron all over, this is dictating, it was his idea that it is dictating the structure of the molecules. So he started to put the valence electron for lithium on a box, on all the 8 corner of a box, because he formed the octet, right? This is the thing he formed. What do you call it? He came out with the idea of octet, that all of them try to fill up the octet and become stable. So all 8 corner, he started to fill up with the available valence electron any atom or any atom, actually elements has. So by this way, he used to put this all the electrons on the corner of this 8 corner box. Interesting thing is, he did not put this, he did not put this electron inside, but at the end or at the corner. He could have put here like inside on the box, and then it would be much more precise, probably more precise. Anyway, so this was his idea, to put and form the octet rule. But again, why the elements or atoms should fall or fulfill this octet? What is the problem for this, that it has to fulfill an octet? We have seen the ionization of energy of the element, right? You see that everything is coming back. That is why we spent 2 weeks on atomic structure. So ionization of energy is if you want to take out an electron from element here, that if you want to take the electron out for helium, neon, argon, we already see that this is a noble gas. This is a very happy, right? They are very happy, and they do not want to be bothered, and they do not want to shed any electrons and so on, and their octet are fulfilled, and they are very stable, right? So they are noble gas. And noble gas, helium has 2 electrons at the end, neon has 8, all right? Argon at the outer shell, there is also 8, and so on. It is all octet are filled up, so it is almost impossible, or not impossible actually, but it is so high energy it will be needed to remove the electrons from these noble gases. And then it comes to fluorine, because fluorine, the electronegativity that we have seen, we will see actually in the next slide, that fluorine is, it does not want to give any electron away. It is very hard to take the electron away from fluorine. Rather, it would need 1 electron to the outer shell or valence shell to become like neon, right? And that is why it is the ionization energy is very high for it. Same goes for hydrogen. Hydrogen, although it is, I mean, ionization energy from, if we go from left to right or top to bottom to top, it increases, right? But hydrogen is always a different case. Anywhere, hydrogen is always a different case, because hydrogen, here we see, is because hydrogen, it does not have any other electron, only 1 electron it has, right? So if it loses the electron, there's nothing, only a proton there. So it does not want to release the electron as well. Okay, another thing, what I was saying that, from fluorine, then it is supposed to increase in this way, but there is some always exception, chemistry exception. And okay, I want to talk about 2 things. If I forget, remind me. Okay, so one thing I'm saying that left to right we go, it will increase, and then from nitrogen to oxygen again, why there is a sudden drop? It was going nice up, a nice trend it was following, but from suddenly nitrogen to oxygen there is a sudden drop. If we look at the electronic configuration, nitrogen is 7, right? Nitrogen is 7. So if we see in this electronic configuration, 1s2, 2s2, 2p6, right? So 1s2, there will be 2 electrons, opposite direction, 2s2, sorry, it will be 1s. It will be 1s, it is 1s2, 2s, and then this is 2p, 2px, 2py, 2pz or z. So there are 7 electrons here, so 2, 2, 4, and then 1, 1, and 1. All right, it does not have to be, you don't have to, I mean, it does not have to be the same way the spin showing. It can be in this way, it can be in this way, it can be in this way. We do not know anything possible, as long as the 2 of the electrons are opposite spin. Okay, for hydrogen, oxygen, if we see, oxygen is 8 electrons, right? Oxygen has 8 electrons, so there will be 2 here, 1s2, 2 here, 2s2, and then 2p. There are 3, of course. First, it will fill up 1, 1, 1, and then the second one is coming here. So in this case, we see that oxygen, it has 2p, right? It is the 2p orbital, and 2px, 2py, 2pz, it doesn't matter that it is in the 2px, it can be 2pz also can have 2 electrons, but x not. But the idea, I mean, the thing is, it will fill up 1, 1, 1 first, and then only it will go to another unfilled. Okay, so since in the 2p there are 2 electrons here, and here it is only 1, 1, 1. Nitrogen just fill minimal requirement. Already nitrogen has minimum requirements, and if you want to take 1 from it, it will not give you, right? If for an example, if your friend, like in the exam, I'm not talking about the very best friend, but let's say that your friend, he has only one pen in the exam, and you lost your pen and you're asking that give me your pen, it is unlikely that he or she would give you the pen, because he has to write for his, I mean, he has to provide his answer. If he gives you his pen, then how he would write, right? Exception are exceptions. I'm not an exception. But that is what they're saying, that nitrogen has the minimum requirements. It does not want to release any more electron from here. But hydrogen, oxygen, it has two pens. So if it even given, it can still have another one. So that is why it is easier to remove this electron from oxygen atom than in nitrogen. And that is why that makes the electronegativity ionization energy a bit less for oxygen than in nitrogen. So that explains this thing in the characteristic. Okay, so another thing I wanted to talk that we are calling it happy group for noble gas, happy group and noble gas, and they don't want to react anything. And the ionization energy should be always high, right? The ionization energy should always be very high for all of them. All of them should be around almost similar for neon, argon, krypton, xenon, and rare. But why it is reducing when we go down the group? Anybody wants to answer? I mean, there is no marks on it here. This is just a discussion. So I would like to hear anything from you. Almost half an hour I'm talking. So would anybody like to chip in here? Anything. You don't have to be correct. If you are correct, then what I'm doing here, right? Anybody? I cannot see your chat box. I am on the full screen and I don't want to go to the chat box, then I will lose all this drawing. Anybody wants to try to describe why it is so? Calling once, calling twice. Okay. So, okay, I assume that you don't know. Now, the thing is, helium has only two electrons. Only two electrons, and then it is in the 1s. It is 1s, so the two electrons are very close. It becomes a panda. Actually, it should be here. The electron should be here, not here. It looks like a panda. Okay, so these two electrons are very close to the nucleus, right? And the nuclear force is too high on this electron. That is why it is almost impossible, not impossible, but very high energy it is required to remove the electron from here. And as we go down the periodic table, we know that their size is increasing because their principal quantum number is increasing, right? The principal quantum number is increasing, the size is increasing. And the size is increasing, and that is why the shielding is increasing for the outer shell orbital, right? As we go down, the size is increasing, so the electrons are getting away and further and further and further from the nucleus. So when it is getting further and further from the nucleus, right, the shielding first is increasing for them, and then second is it is far away from the nucleus, and that is why it will be less what do you call it, energy to pull the electron out from that far orbital. And this thing will also describe the electronegativity as well. Electronegativity is the opposite thing for ionization energy. That means how hungry one element is for an electron. how hungry for an electron one atom is, or one element is, for an electron. And there is no unit for it, and there is no scale for it. Scale is actually a Pauling scale. It's put on the Pauling scale, and then on that scale, fluorine is kept for the highest. So we have already discussed about it, and you can relate to this ionization energy. So the thing is, when there is a high electronegativity, that means they will try to snatch the electron away from others. Okay. They will try to snatch the electron away from others. And in this race, fluorine stands the first. Why? Because fluorine wants to become like neon. If just one electron it has, then what will happen is it will be like very stable. It does not have to think about other thing. It can just chill, and that is why it will. And another thing that helps it to be more electronegative is the compact size of its atom, because fluorine has 9 what do you call it, atomic number, 9 protons and neutron in the atom, and it is in 2s. The period is 2, right? So it is comparatively is smaller in size, but there are many more of the nuclear particles in the nucleus, so that it can attract more electron towards it, and that is why it is high. So when those are the extreme left, and another thing is helium, neon, argon, they do not have electronegativity, because they do not want to have any electrons already, because they are already very happy, right? But krypton and xenon, they want more electron. We will discuss later on when we talk about the structure. Okay, and what I was saying. Oh, so on the extreme right, that is the electron negativity is high. On the extreme left corner, bottom, the electronegativity is very low. So what is this? That electrons, they all of them try electron hungry. They want to take the electron. They themselves try to, they want to release the electron. And if we look at the periodic table as well, we will see that if they just take 1 or 2 electrons, they will become the noble gas configuration. And if they release 1 or 2 electrons, they will become noble gas. So that is why they are so interested to release, and that's why they are so interested to take the electrons. Okay, so that is the thing, that electronegativity. And because of these electronegativity differences, the higher the difference, the more stronger the bond is. Like, I need more of it, and somebody wants to release more. Of course, we will have the bigger bonding, right? And those who say, okay, I am okay, if you give, if you don't give, you don't give. So in that way, it will be not that strong bonding. So can you relate to our human behavior to this thing as well? Right? So we have become more best friends, or good friends, good bonding, good partners, when there is a need between us that we have to have a bigger need, rather than just some small needs or some few things. Okay, so Lewis dot. If we understand this valence electron, sorry, not valence, electronegativity and ionization energy, then we can move on to these Lewis dot symbols. And for that symbols, Lewis, Gian Lewis, he on the periodic table, he showed only the valence electron by a dot on the periodic table, that which of them has how many valence shell electrons. Okay, so in this way, we see that hydrogen has 1, lithium has 1. So 1A all have one valence electron. 2a has 2, and we will not consider this one right now because this is transition and this is a D block element, so we will not talk about it later maybe. And this 3 or 13 in modern periodic table, we call it 13, 14, 15, 16 in this way. But in old periodic table 3a, they have all three, in all of them has 3 valence electron, and 4 they have 4. So in this way it will go on, and Lewis, he put these electrons, the dots, to represent the valence shell electrons at the outer shell of that elements or atoms. And the unpaired electrons can be used to predict the number of bonds that an element will form in a compound. So when there is one, most likely, they will form one bond. When there are two, they will form 2 bonds. When there are 3, 4, but when there is 9, will they form 9 bonds? No, again, they need just 1, so they will form 1 bond. The difference from what they have and what the octet rule should have will be the number of bonding, and that is why the octet rule came out. So octet rule refers to the tendency of an atom to prefer to have high 8 electrons in the valence shell, and no matter what, we have valence shell that S, P, and D. So D, it can have more than 8 electrons. It can house more than 8 electrons. So that is why D block elements are excluded from this octet rule, strict octet rule, because this valence shell electrons, it includes the S and P elements, block elements. Okay. So when they filled up the octet, they will achieve the maximum stability with lower energy, just like noble gases. And to attain the octet, they will lose, share, and gain electrons. And it is S and P. P involves electrons, and so it is not used to predict the tendency of transition for bond formation. Okay, so in this now, I will go to see if anybody has any question. No, Mohammad Usman, sir, please check your email. I will after the class. If you have anything, you can also talk here. And I'll go to some Menti questions. Please go to the Mentimeter. I have prepared, not yet. We have a few Menti questions today, quiz, and please go to the Mentimeter and use this code. It's quite easy question for you guys to take, I'm sure, but at least this is the code. Use this code and give your answer. Okay, are you on? Go to Mentimeter, please, and then use that code and cast your vote or click on the right answer that you think. And your time will start soon. There are 20 students here. I want to see all of them are participating here. More, faster. 30 seconds. 20 seconds. 10 seconds. Faster, 10 seconds. 5, 4, 3, 2, 1. So those who are not participating, what are you doing? You are not on computer or what? So this is the correct answer, the 7. Okay, this is the correct answer, because from the periodic table we also can see that it has, where is it? From periodic table, just now we saw that here fluorine has 7 valence electron, and it is in 7A. So all these fluorine, chlorine, bromine, iodine atom, so these all are halogens class, and every one of them has 7 electron each at the valence shell electrons, at the valence shell. Okay, so those who got it correct, thank you. I think most of you have corrected it. All right, so now we have seen the octet rule and formation of ionic bonding. Formation of ionic bonding, of course, refers to the electrostatic force between cation and anion, and ionic bonds usually form between metals and non-metal atom. So I cannot see your chat box, but can you say why it is favored between metal and non-metal? The ionic bonding, why it is favored between metal and non-metal atoms? Okay, it is already given actually, the answer. So it is non-metals used to take the electrons, and metals used to take, give the electron or release the electron. So for metal, those are transition metal. We're not talking about the transition metal per se now, but for the alkali metal or alkali earth metal, that is the 1A, 2A groups, and for the non-metals, that starts from 5A and so on. So those who wants to take the electrons are non-metals, and those who wants to release the electrons are metal, and that is why between them the bonding is quite strong, and they will form a bonding. Okay. In the process of gaining and losing electrons or electron transfer, both metal and non-metal atoms gain complete electron shell by, we have seen it, that by sharing the electrons or transferring transferring. We are talking about the ionic bonding. So transferring the electron by giving or taking, they are forming the bond. And if we want to see the example for it through the Lewis dot, we will see the formation of cation. Lithium being in the group 1, it is having 1 electron at the outer shell, and it is releasing that electron because it is easier for it to release and becoming a helium structure or noble structure. That is the simple thing is it is a metal, so it is easy for it's easy for this lithium to release one electron, and it will release that electron and becomes a lithium ion. And since it is releasing the electron, fast ionization energy is 420 kilojoule, quite, I mean, not that high, is okay. And formation, and fluorine, it is very much electronegative, so it will take that electron. This electron is here, this electron, it is here coming, and then fluorine is taking that electron and forming the lithium fluoride ion molecule in this way. So the fluorine has a electron affinity is very high, which is to take, for affinity for an electron is very high, so it will of course take the electron. And lithium fluoride compound will be formed. So in between them, if we see the difference of electronegativity, we'll see in a bit. The difference is quite big for the electronegativity, and since the electronegativity is big, the electrostatic force is also big, and that is why they are ionic bonding. But when they form this compound, lithium and fluoride, if we look at the ionic electronic configuration, we'll see that 1s2, of course, it is 1s2. Previously, it was for lithium ion, it was 1s2 and 2s1. This one is this electron, right? It is in 2s. And for fluorine, it was 7 electrons. So 1s2, first one is filled up. 2s2, this is filled up as well, but this is not filled. This is one was short. So now when they fill up this lithium fluoride, it becomes this electronic configuration is for fluorine 1s2, 2s2, 2p6, and this is for lithium, that is 1s2. Both of them are, this one is achieving helium structure, and this is achieving neon structure. So in this case, we call it that lithium in this state, lithium positive or lithium plus, becomes the isoelectric of helium. Isoelectronic configuration for helium, it forms isoelectronic. Okay, so lithium plus is isoelectronic to helium, and fluorine fluoride or fluorine negative is isoelectronic to neon. Okay, to isoelectronic to neon. So this is isoelectronic, means electronic configuration is same. Although they are charged, they are ionized, they are not on the stable state, but still they are ionized. In that state, their electronic configuration is same like the other one. So when we when it is said that okay, write the isoelectronic configuration for them, for that, which one is isoelectronic for this, so you can see the electronic configuration, you can write the electronic configuration and see which one is isoelectronic to which one. And when they form this lithium fluoride, they will, this type of electrostatic force they form, due to that electrostatic force, they will form, and they, because of that, they try to form a crystal, and that crystal, if we can make it bigger or see it, we will see in this way the crystals. So lithium fluorine is always bigger than lithium, because lithium has only 2 electrons. Here lithium has 9 outer shell, so that is why lithium fluorine is of course bigger a bit than lithium, and it is where that is why it is shown. And fluorine negative is bigger than fluorine, right? Fluorine negative is bigger than fluorine because when it took one extra electron, it to accommodate that extra electron, it has to be expanded a little bit. So it is, even though a very, I mean, small difference, but it should be a bit different because of this extra electron it has. And same thing will go like potassium. If it is potassium positive, it will be smaller than original, mother element or original element potassium, because it is releasing one electron. When it released one electron, of course it will be a little bit smaller than that original one. So how the energies are working here or playing out for this ionic bond formation? What is the energy diagram looks like? What does the energy diagram look like when the two elements comes together and form a bonding? For sodium and chloride, again, it could be lithium and fluoride. We could have shown it in lithium and fluoride, but this picture is available in the book, so I took it. And sodium and chloride. So sodium, when it is releasing one electron, it becomes smaller, and chloride, when it took one electron, it becomes a bit bigger. Right? To house that electron, extra electron, it becomes a bit bigger. So when the sodium and chlorine, chloride is very electronegative, sodium is less electronegative, so sodium wants to give the electron to chloride, and chloride wants to take the electron from sodium or anyone, so that it will be easier for to make them a bond. Okay, so but when they are forming a bond, how do they form a bond? They have to come close together, right? In any other example, you can see that if we have to make a bonding, we have to be connected. Of course, it's a pandemic time, but we can be connected through many other platform, the digital platform, many other ways, right? We can write a letter as well, but I don't think people write a letter anymore, but we can write emails or on those ways. But the point is, we have to come close to each other to make a bonding, right? So when they come close to each other, what is happening? That sodium, it has, after releasing one electron, it has 10 electrons in it. Sodium has 10 electrons in it. And chlorine, after taking one electron, it has 18 electrons in it. And okay, let's just talk about the valence shell. Okay, so sodium has 10 electrons, chlorine has 18 electrons in it. And because of this, it has 11 protons, it has 17 protons and 17 neutrons or something like that, and it has a nucleus consisting of that 11 protons. It has a nucleus consisting of 17 protons. So the nucleus is positively charged. Right? Nucleus is positively charged. So even though it is negative, chlorine is negative, but they have positive nucleus. So when they are coming very close to each other, and that distance between them is smaller than their radius, how to say, when they are infringing the barrier of their the boundary, the positive force of the nucleus will repel each other. because nucleus is always positively charged, so it will not allow two positive charged nucleus cannot come close together, right? So they will repel each other, and that's why a repulsive force is increasing. Repulsive force is increasing in this, and you can see it is actually very high, and it shoots up like a rocket at less than this distance. This distance r is the distance between these two here. This is the nucleus, this is also nucleus, so this is the distance between them, right? This is the sum between them, this is the distance, so this is r. So the radius of both atoms are added, plus sodium plus chloride. So if they come more close, less distance than these two, there will be a repulsive force because of this positively charged positively charged nucleus that they have. And what I was saying that, okay, and then it is from here, it is almost the same. It does not change much, only a little bit. Maybe it is exerting more pressure here. And when we go beyond that distance, when we go beyond this distance, so from this point, you can see it is almost, it didn't change. The potential energy is increasing too much. It's like shoots up. But again, if we move away from one another, like this one, to distance, the distance between them is very big now. It is r, let's say I put it capital R between them. It's very big now. So it does not have any potential energy between them. It's zero potential, almost no energy between them, right? When it becomes very, far apart, they are falling far apart, all right? But at some point, they are at a distance when this is the potential energy is minimum. Potential energy is minimum. So they are forming a bond. They are forming a bond, and the potential energy is negative. At this negative energy, of course, because of negative energy means they are so much stable that first of all, you have to take out this much energy, or this much energy you have to provide to bring them to zero. Later, you have to put more energy to have them repulsion. So the lowest energy they have is at this length, at this distance, all right? At this distance, that is 236 angstrom. I think it should be in angstrom. Distance, picometer, sorry, is 236 picometer. When there are difference between them, they are more stable. But anybody can ask the question that what's wrong if we have zero potential energy, and then why are they not making a bond between them? When they have a potential energy of zero, that means, okay, they are stable, good, but they do not have any, what the word should be, they do not have any urge to make the binding. They can stay alone and stay healthy and stay individually and stable. Okay, so they are coming close and bouncing to each other and then going out again, and then so they do not have any interest when there is potential energy. That's neutral, both of them are okay. But when they have less, the lowest potential energy, at this moment when they found that okay, it is much better to stay together and having the lowest potential energy and more stable than staying alone, being charged. Okay, because when they are at this moment, at this state, and when they are charged and potential energy is zero between them, there could be other element who will come and disturb them. or other charges, there can be. So that is also, if even 0, they are not that stable. But when they are the minimum potential energy, they are very stable this way. Okay, and this stability or attraction force between them can be expressed by some equation, that is E, the strength or electrostatic force between them, is proportional with the charge of the ions, okay, and inversely proportional with the internuclear distance. So when the internuclear distance becomes too big, so the E will reduce, all right, the E will reduce. And when this one becomes bigger, these two becomes bigger or more, Q1 and Q2, E2 will also increase in this way. Okay, so Lewis dot symbols to show the formation of aluminium oxide, Al2O3. Aluminium 2, there's Lewis dot. First of all, we have to draw the valence electron for aluminium and oxygen. And aluminium is a 3A, so it will be 3 dots or 3 valence shell. Oxygen is 7A, so there are 7 electrons, outer 6. Fluorine is 7. So 6 valence electron at the outer shell. And this is the mineral of corundum, or it's aluminium trioxide, dialuminum oxide. Okay, so now if they want to form a bonding between them, alumina and oxygen, what is the problem is it has 3, right? It has 3 and it needs another 5, and it has 6, right? It has 6, it has 6 and it needs another 2. Needs another 2 to make a stable state, all right, or stable configuration. So what will happen is if they just react to each other, aluminium, what will happen? Aluminium give all 3, it does not make it 8, and if it gives all the 6, although it's impossible, but if even it gives all the 6, it does not make its octet filled up. So what will happen is if 2 aluminium atom comes in this state and they react with 3 oxygen atoms or oxide, and then they can form in this way, and by this formation both of them will have the highest stability, that is the neon formation. And that is why this 2 is added here. 2 aluminium atoms are reacting, 3 oxygen atoms are reacting, and at the end, when we are writing the structure of the chemical alumina, that is 2 aluminium oxide, 2 aluminium and 3 oxygen atoms. So Al2O3, if you write Al3O2, this is totally different thing and it is totally wrong. That means 3 aluminium came here and 2 oxygen was involved. That is not the case, right? So if you write in this way, it will be wrong. Okay, so there is a question here. It says that is the electrostatic force between aluminium and oxygen ionic bond stronger than that of sodium and chloride? With this, I will take 5 minutes break now. Okay, I'll take 5 minutes break, and please reply. You can type your answer in, because I can see your chat box now. If you want, everyone, please try to answer. What is your answer for this question, that is the electrostatic force between aluminium and oxide ionic bonds is stronger than that in sodium and chloride? What do you think? Yes or no? Okay, yes or no question. So 5 minutes break. By this time, please try to keep in your answer, your voice. All right, so I'm back and I can see 2 of you have replied, Jason and Tiffany. Thank you very much, both of you. What about others? It's just yes or no. If you don't say yes, say no. If you say no, then I'll say yes. So even yes, no answer, you also don't want. Jonathan, thank you. Liao Zixing, Daniel Clarence, aluminium stronger, Amanda Michelle. Wow, thank you so much. Thank you so much for your answer. Yeah, I'm really happy that so many of you has participated. Okay, good. Yes, but why? The thing is, it is, I mean, we can just say yes or no, but we have to know why it is stronger. Why is it stronger than sodium and chloride? The answer is, we don't have much time, but the answer is that aluminium is having 3 and oxygen is 2. So they are more ionic character, not character, I mean, what do you call it? They have more thing to number, not number, what I'm saying actually. Okay, so okay, what is said? Anupaja, number of electrons. Yes, number of electrons are more in this, involved in this, and the electrostatic force is increased because the charge is more. It has to share 3 electrons, it has to share 2 electrons here, whereas only 1 and 1. So their charge is more. So if you invest more money, of course you will expect more return, right? Or if you invest $1 million, let's say, then you would be expecting, or you would be more cautious, or you would be more serious in getting that back, rather than someone is investing only $1, right? So that is the thing actually. If there is more charges, the electron has been involved, so it's more. All right, so now let's move to the properties of ionic compounds. Ionic compounds are, due to this thing that they change because of this, they transfer the electrons. So that is why their property, I mean, they're more strong. The bonds are usually, yes, it is usually more strong than other bonding. And that is why they appear crystalline solid. And because of this crystalline solid, they are, since it is crystal, right? What do we know about crystal? Let's say it is just one example I'm giving. Like this is a crystal, this is another crystal here, this is another crystal here, right? This is just an example. So all the crystals, so it is, since it is crystal, it is brittle. It can be broken because through this crease, it can be broken. So it is brittle. But again, it is having high melting temperature. Why? Because you have to remove, to melt it, like let's say sodium and chloride, for example, sodium and chloride. To melt it, this, you have to remove these two both from one another, and sorry, it's not melting, it's dissociation. I'm talking about melting, it's not melting. Okay, so for melting, it will be, since it is brittle, and melt means it will be in liquid state than in solid state. So it has to be, the electrons and all those things, that the structure, the brittleness has to be in a way that it becomes more soft. To make it softer, you have to have high temperature, and because of this ionic property, it is having high melting temperature. It is electrical insulator when in solid state, right? When in solid state, sodium chloride, if it is solid, it is an electric insulator. It does not conduct the electricity. And do not try this at home. This is from the book, if your sodium chloride is very much pure and it is 100% solid, then it should not conduct an electricity. But at home, that sodium chloride, the table salt that we eat, who knows, maybe that is not 100% pure, who knows, or probably it is not 100% in solid state. So if you do not try this at home, but from the reference, we know if it is an ionic compound and it is a solid, then it would not or it will not conduct any electricity. But if it is dissolved in water, it is a very good conductor. It is a very good conductor. It will conduct because of their charge. They have the electron, available electron, so that they can conduct the charge. So these are the explanation just now I gave. So if we ask you in the question that what are the properties of the ionic compound and explain, and somebody writes, okay, it is brittle, high melting temperature, electron insulator, he or she will not get marks. Of course, maybe it will only 10%, 20% marks they will get, but not 100%, because this is the description. It is not the explanation, right? You have to explain. If we ask you explain, you explain why it is brittle, why it is high melting temperature, why electrical insulator. All right, so these all are, we talk about the ionic bonding. Now let's move to the covalent bonding. Why there should be another covalent bonding we have to consider? Because in organic chemistry, mostly in organic chemistry, when we will start after week 7, hopefully, and if everything goes fine. So organic chemistry, mostly carbohydrate, carbon and hydrogen, right? Organic chemistry, mostly carbohydrate. And of course, there are some other elements, nitrogen and sulfur and so on, but mostly carbon and hydrogen. And then it does not explain, it cannot be explained, the bonding and their characteristic, by ionic bonding. So it has to be some other explanation for this type of bonding, and that is why Lewis comes out of this, and then they say that, okay, there might be sharing of electron as well, and that is how they are forming the bonding, and that is called covalent bonding. For example, here is one carbon. Carbon is 6A, right? Carbon is 6A element, and it has 6 orbit valence shell electron, right? 6 valence shell electron. Hydrogen has 1 at the outer space, outer shell. So what will happen is hydrogen needs 2. Hydrogen needs 2, so it becomes a helium, and carbon needs 4. It wants 4 to become neon structure, stable structure. So each can, but it cannot snatch a hydrogen element from, electron from hydrogen, because hydrogen and is not that less electronegative, and carbon is not that high electronegative in compared to hydrogen. So what you do, okay, come to an agreement. Let's say I don't snatch your, but it will be beneficial for you, for me as well, so let's share. So that is how they will share. And these 2 electron, although it is shown in here, it is not only here. Both electrons belong to hydrogen and also belong at the same time belong to carbon as well. So this 2 electron is roaming freely in hydrogen and carbon at the same time. Same thing goes for this. So these 2 electrons are being shared by these 2 atoms. All right, so in this way they are forming a bond, and this is how they are forming CH4, and this is the simple methane gas. They are forming a methane gas, CH4. All right, so this is how the covalent bond is formed. It's quite a simple thing, and from the Lewis theory, again, we can see about the oxygen and nitrogen formation, right? So oxygen, when they are together, there is no other thing, there is no carbon, no hydrogen, no other elements together, so only they are two, both of them are together. So they will come together and share their own electrons among themselves. So oxygen needs 2 more electrons to form inert gas structure. It will form this. They will share these 2 electrons. So these 2 electrons are shared between them. Nitrogen being in 5a, they need 3 more electrons to be shared within them, so they become neon structure. So they share these 3 electrons, and that is why they form 2 bonds here, and oxygen 2 bonds. It's shown in here, right? Oxygen 2 bonds they share, and nitrogen they form 3 bonds between them by sharing. So when they share 2 electrons, there is 1 bond. When there is 4 electrons shared, there will be 2 bonding. When there is 6 electron sharing, there will be 3 bonding. So here 1 bond represents 2 electrons. 1 bond represents 2 electrons, right? So when we say HCl in this way, and there is 1 bond, a bond is usually shown by this dash line. So we understand that there are 2 electrons in 1 bond that is being shown. Okay, so this is 2 electrons are here. Typical bond formation for main groups elements that we can see here, that carbon and hydrogen and chloride. So there are 2 bonds in this bonding, and there's 2 electrons in this bonding, and these both electrons are belong to this hydrogen, and also both electrons belong to this carbon as well at the same time. It is not like chlorine is having these 2 electrons, so hydrogen at a moment is without. No, it's not like that. At the same time, they are having the both electron. It's up to your imagination how you want to imagine it. Okay, and then group 6A, there are 2 oxygen needs 2 electrons, right? It needs 2 more electrons to form an octet. So it will bond with 2 hydrogen, and there are 2 electrons here, 2 electrons here. In this 1 bonding represents 2 electrons, so that 2 electrons, it will, at the same time, it is having 8 electrons, right? 2, 4, 6, 8. At the same time, hydrogen is having 2 electrons, and this hydrogen also are having 2 electrons. So this is how they are forming the bonding. And this is also the Lewis structure. This is also the Lewis structure, and Lewis structure tells us or gives us a hint, or actually it gives us a very good idea of what structure for that compound is plausible or possible, or will be more stable. In this way we can write. If we would just write oxygen and then we show the 2 bonding without showing the other electrons around it, we would not be able to understand what is the difference between this and this, right? What is the difference between this and this? If we do not show the other electrons around it, we would not know whether it has forming octet or stable or not. So Lewis structure, and that is why this is very important for us to know and to draw and to understand the Lewis structure. So drawing the Lewis structure, there are some rules for the drawing the Lewis structure. We have to arrange the skeletal structure of the compound, and this is important, less electronegative element will be at the center. If we see here, we will see more of that, more of the examples later on. But when we see this thing, carbon dioxide, oxygen is more electronegative than carbon. So this carbon is in the center. Here as well, carbon is less electronegative than hydrogen. I'll come later for this one. So carbon is less electronegative for this from oxygen, and that is why it is at the center. Same goes for nitrogen is less than oxygen, so nitrogen is at the center and oxygen at the outer side. But hydrogen is always left at the outer side. Is not, we never put hydrogen at the, even though it is fluorine, whatever, or here, or any other atoms that we are discussing on nitrogen and carbon and oxygen, hydrogen will always be, even though it is less electronegative, it will be always outer side, because hydrogen can form only one bond. Those who will be at the center, they will be able to form more than one bonds. Okay, that is the idea. That is why the less electronegative is kept at the center. Okay, so we have to count the total valence electron. Like for carbon is 4 group, so it will be 4 electrons at the end, and we have to draw the one single line to mark there are 2 electrons at the end, or one bond will, one line or one bond, it will represents 2 electron, and the remaining electrons we will be adding around the atoms, okay. The less electronegative, the rest of the electrons will be adding around the atoms. And if adding and drawing this bond does not satisfy the octet, what we will do is, if there is available electrons, we'll try double bond. We'll try to draw double bond or triple bond together. For example, here, nitrogen trifluoride. All right, what's the time now? Nitrogen trifluoride, and nitrogen is less electronegative than fluorine. Of course, that is why nitrogen is at the center and fluorine is around it. So what we'll have is that we will count the valence electron. Okay, we'll count the valence electron for all of them and sum it up. So valence electron for nitrogen is 5. Nitrogen is 5 for valence electron, and for fluorine it is 7, right? Fluorine is 7, but there are 3 fluorine atoms, so multiply. So altogether there's 26 valence electrons. So what we'll do is we will try to put all these 26 electron all around it. Okay, all around it, this 26 electron. 2, 4, 6. So 3 times 6 is 18, then 20, 22, 24, 26. So it satisfies all these 26 electrons, and all of them are octet filled up. So this is nitrogen has 2 plus 2 plus 2 plus 2. So nitrogen has 8 electrons, fluorine has 2, 2, 2 and 2 as well, so 8. So all fluorine and nitrogen, every one of them has 8 electrons around it. So this is, all of them has filled up the octet. Now it says that nitric acid. So what we'll do is, which one is the less electronegative? Hydrogen. But hydrogen, as we know, that we cannot put hydrogen at the center, right? Because hydrogen cannot form more than one bond. So if we put one at the center, hydrogen will stuck there. So that is why hydrogen cannot be put at the center. So nitrogen is less electronegative. This is exception, yeah? So hydrogen cannot be put in the center. Nitrogen is less electronegative, so we'll put nitrogen at the center and oxygen all around it. And later on, hydrogen, not necessarily with this oxygen, this hydrogen can be put here or can be put here. Doesn't matter, the same thing. Okay, so So nitrogen and oxygen all around here, and then we have to count the valence electrons. So valence electron for nitrogen is 5 and oxygen has 6 each. Each of the oxygen has 6 electrons. There are 3 oxygen atoms. So multiplied by 3 plus hydrogen has only 1 electron at the outer shell. So there will be 1 electron for hydrogen at the outer shell, and that is why it will be 26 altogether. What we'll do is we'll try to form a bonding between them like this. At first 1-1-1 bond, and put the rest of the electron around it to make it 24. So 2, 4, 6, and then this 2, 8. 2, 4, 6, and then this 2 is 8, 2, 4, 6 here in this bonding, and then 2 here, so 8. So for this we see that all of them are forming a bond. 8. This is 8, this is 8, this is 8, and hydrogen cannot have 8, right? Hydrogen, there is another exception. Hydrogen cannot have 8. Octet for hydrogen means 2 electrons, and hydrogen is happy having helium structure here, 2 electrons. So hydrogen is also filled up, cannot take more. So there's the problem is, this one is okay, this is okay, this is hydrogen, okay, but nitrogen has only 6 electron, 2, 4, 6. So there is another 2 is left for hydrogen, nitrogen. For 2 is left for nitrogen. So what we will do is these 2, let me just erase it, some of it. So nitrogen, since nitrogen cannot or does not fill up, yeah. This is, yeah, Daniel's, yeah.
Who's supposed to say nobody?
Sorry?
Anybody supposed to be sitting there?
I don't know, because after Daniel left, it is here already. I mean, it's been here. And this is like Tingsun, but I haven't.
Tingsun is there, right?
Okay, sorry for the interruption. So here, this is octet filled up. This is octet filled up. Oxygen is also octet filled up, but nitrogen is not. So what we'll do is, since these 2 electrons are available and oxygen is not using them anyway, it will just chip in here to help nitrogen being stable to fill up this octet, nitrogen octet. So these 2 electron, all these 2 electron is from oxygen. This is another interesting thing actually. We can talk more about it, but I don't want now. Oxygen being very electronegative, still it is so good and big hurt that it is giving these 2 electron here to make nitrogen fill up this octet. Okay, nitrogen fill up this octet. By giving these 2 electron, nitrogen is sharing, and oxygen of course is having it. Nitrogen is also sharing. So this is not 1 from nitrogen 1. So bonding can have 1 from nitrogen, 1 from other, let's say not chlorine. What can I say? Hydrogen as well. Okay, so 1 from each. 1 from each, the bonding can occur. Another way bonding can occur is oxygen can give both of its electron to nitrogen, both of it to nitrogen, sharing. I mean, this is not giving all that, everything is, I mean, how to say, is not giving for forever. It is just helping it to be stable. Why? In this way, if nitrogen becomes stable, this whole compound becomes stable, and then this oxygen will also be stable. So this bond does not have to be formed here. It can be happening from this oxygen as well. It's not necessarily on this bond, on this oxygen atom only. Okay, so and this is why This is how they will be, the octet will be formed, and still they will be having more, I mean, all of them will be having octet filled up. Only one thing is here, when you see that there are 4 electrons here, there are 4 electrons, available electrons, there are 6 available electrons are here. So nitric acid, in this is why nitric acid oxidizing agent, and they have a lot of electrons, available electrons on them. When we start reading more, maybe we'll discuss more about it. The structure of carbonate ion, I am not going detail into it. You can try, okay, later. So formation of covalent bond. Again, there is a valence bond theory. The repulsion, we call it valence bond repulsion theory, VSPR. So here, according to valence bond theory, they said that localized electron pair theory, a covalent bond is formed when orbitals from 2 different atoms overlap, with each region of overlap accommodating a maximum of 2 electrons of opposite spin. So let's say this is the 1s and this is also 1s. When they are forming an orbital, they are not in the original shape of that atom, right? 1s and 1s, they are forming in this way, and all together they are forming one big type of orbital, and the whole electron cloud is now belong to them. It becomes bigger and it belongs to both of the nucleus, these 2 nucleus. And when there is overlapping, this is called overlapping, and when there is overlap, if 1s, only 2, whatever it is, 1s or 2s or 2px, they can overlap, but every one of them will have maximum 2 electrons there. So this is the valence bond theory, okay? Is called, and from the energetics of the covalent bond, it also similar to that of the ionic bond that we are forming. We just now have seen at there is a minimum point where they will form a stable bonding. Some general properties of ionic bond and covalent bonding. So sodium chloride and carbon tetrachloride, they are 2 different bonding, and sodium chloride is ionic, and this is covalent COV anyway, covalent bonding. It is a white solid type of thing that we have discussed, that the covalent, ionic bonds mostly are solid and brittle, and that is why you see that it is whitish solid, that the table salt that we have seen, we will see in our on our kitchen. But our kitchen table salt also has some other impurities because it is taken from the sea. So nowadays a lot of plastics. And carbon tetrachloride, it's colorless liquid, all right, and because it's covalent bonding, so it is a colorless liquid. It didn't form a solid. Melting point, it is 801. See the difference. 801 degrees centigrade for this sodium chloride to be melt. For carbon tetrachloride is -23rd, is -23rd. Okay, so it's room temperature, it is already liquid vapor. Okay, and molar heat of fusion is also very low. Boiling point, of course, it will be more high, because if the melting point is 800, boiling point is density. Again, the density, since it is a solid, density is higher than that one. Solubility in water is very high, this is interesting thing, the solubility of in water, because of sodium chloride's ionic bond, they form ions, right? Sodium plus and chloride negative. So they, since they are ionic in character, solubility, water will be ionic as well. Water is also ionic in characteristic, so they will try to dissolve the ionic compound, because in chemistry we call there is a rule that like dissolves like. So if it is an ionic compound, ionic solvent will dissolve it. If it is non-ionic solvent will dissolve it. All right, types of bonding. And now if we want to see the differences of the bonding, or if you want to dissect the bonding, how the bonding is happening. Ionic bonding, mostly metal and non-metal, they are forming ionic bonding. But covalent bonding is mostly non-metal and non-metal. They are the covalent bonding forming, and there is no 100% ionic bonding or covalent bonding, but they do not have equal sharing, because covalent bond, they have we say that they share the electrons, right? But there is no 100% like I share 50%, you share 50%. No, not in this way. There is no 100% covalent bonding. There is always a partiality in sharing the bonding. All right. So electronegativity and bond polarity. So as the electronegativity increases, the bond polarity will also increase. And when the bond polarity increases, the ionic character of the bond will also increase. If we put it on the electronegativity chart, the ionic character of the bond, we will see that on the extreme left up top, because there is the electronegativity difference between them is very high, so they are more ionic bonding. And the electronegativity difference, if the electronegativity difference in the bond between the atoms attached in a bonding is more than 2, then it will be ionic character. For example, lithium and fluoride, let's say, you see here lithium is 1 electronegativity and fluorine is 4. So between the difference is 4 minus 1. So it will be 3. And we always take the mode of it. So there is no difference in no sign. There is only the neat difference. There is no sign shown. So the difference is 3. And of course, it will be ionic bonding. But if lithium and beryllium is form a bond, beryllium is, or magnesium, let's say lithium and magnesium is forming a bond, 1.2 minus 1, so it is 0.2 difference. So in this case, the bond will be non-ionic, because ionic, it has to be more than 2. Electronegative difference has to be more than 2. Then it will be 2 and more. It will be ionic bonding. And if it is less than 2 and 0.5, less than 0.5, precisely 0.5 or 0.4, sorry, precisely. If it is less than 0.4, it will be covalent bonding, and in between them there is, we call, polar covalent bonding, 0.5 to 0.2. In between them it will be called polar covalent bonding. If you have this chart in front of you, you have the calculator, try to find out the difference between them. You will see that polar covalent bond, all these things happening. So this is what we see. Okay, now classify the following bond as ionic, polar, covalent, or covalent. The bond in HCl is electronegativity difference is 0.9. So when it is a 0.9, it will will it be an ionic or a covalent or non-covalent? Since it is less than 2, it is not an ionic bond. If it were more than 2, it would be ionic bonding. And since it is more than 0.5, so it is a polar covalent bond. Potassium fluoride. So the difference between them is 3.2, so it is an ionic bonding, and carbon tetrachloride should be, is it? And HCCCH CH3, CH3, carbon, and ethane. Two of them, the difference of the bonding is 0.00. So we see that the bond is non-polar covalent. And increasing electronegativity for all these things. So you can have it, you already have it in front of you, so you can just start. Octet rule we will try tomorrow and we'll finish. There will be interesting thing about octet rule, and there's the Lewis structure, and then exception is octet rule to Lewis structure, all those things. But I want to do some Menti question now yet again. Go to menti.com. And press or use this code. I paste it here in the box, chat box. I paste this. So use this code and answer. Provide your answer. We do not have much time, so I will not stop. Maybe 1 minute. Which of the bonding takes higher energy to break? Nitrogen, oxygen, chlorine, or HCl? Oh, okay, 1 minute you have. Okay, 30 seconds, almost going, finish. I should give only 30 seconds, yeah. Okay, voting closed. 11 of you has given HCl, 2 nitrogen, 1 is chlorine. So the thing is, like what we're saying that just now in the here, that the bond between them, the electronegativity difference, so the higher the electronegativity difference, the stronger the bond is. For example, HCl is, where was it? H and Cl. Okay, from here you can find. How can I remove this? for here, H is 2 and chloride is 3. So between them is 0.9. The difference is 0.9, right? And it is not an ionic bond. It's a very polar covalent bond. And then in between them, they have 2 electron sharing. That means 1 bond. However, for nitrogen, we see that in 2 nitrogens, how can I draw? Just draw this way. Okay, for 2 nitrogen, why is okay, whatever. So between 2 nitrogens, we see that they are nitrogen, and there are, although the difference between them is 0 because both of them has 3 electronegativity, but both of them has 3. But there are 3 bonds between them to break. You have to break 3 bonds between them. All right. So it is not only depending on the electronegativity. Okay, there is structure as well, and that is why if we would just do the electronegativity difference and ionic bonding, and we know the ionic bonding and all those things, and it would be so easy for us to understand, but it does not explain the thing. So nitrogen is higher energy. It has to have higher energy. You have to have to break the bond between them, and that is why we should learn, or we should know more about the structure, the Lewis structure, and Lewis, that is why Lewis is so important for us. Okay, so another question is this one. Give your answer. Type in, just take this and paste it in the menti.com, and then we will see what is the answer for it. Okay, you don't, I have just 1 minute. Do it faster. Which of the following is correct? Lithium hydrogen or lithium hydride is a polar covalent bond. Sodium iodide is a covalent bond. Carbon nitrogen is a metallic bond. Carbon monoxide is a polar bond. Faster, faster. If you look at the electronegativity table, then we can find out the lithium and hydrogen, the difference is 1.1. So it should be what? Ionic bond, right? Or polar covalent bond. What? Which one? One minute. And another one is lithium hydride. Another is, what is that? Other option is sodium iodide. Sodium is 0.9, iodine is 2.5. So difference between them is 1.5. It's not a covalent. Carbon nitrogen is a metallic bond, is it? Carbon and nitrogen is not a metallic bond, because carbon and nitrogen, the difference is 0.9, but they are, both of them are non-metal, so it cannot be a metallic bond. Carbon monoxide is a polar bond, is it? Carbon and oxygen, the difference between carbon and oxygen is 1, right? So will it be a polar bond? Okay, time's up. So actually, it is shown in this way, but this is also true. This is also true. I did not calculate. So those who 5 of us choose the first option, lithium had a polar covalent bond, you are correct. I did not look at the electronegativity. So the difference between lithium and hydrogen is more than 0.5. So it should be a polar covalent bond. So it is correct. But this is correct as well. This is a polar bond. And those who 9 of us replied, this is the correct answer. Thank you. Because although they are, the difference between them are less than 1, right? Less than 1. So still, because of their, I cannot draw it here, but tomorrow I'll show you. This carbon in the center, 2 oxygen on the other side. So because of their structure, oh, I'm showing the Mentimeter, okay. Because of their structure, they are a polar bond, okay, although it's not an ionic compound, but it's a polar bond between them. Okay, so I'll see you tomorrow after, at 1 p.m. All right, tomorrow I'll see you at 1 p.m. So, any questions so far? Okay, so see you tomorrow. Thank you for attending. Okay, all the best. Bye bye.